We are starting to round up our study of the periodic table. Now, obviously, we'll keep referring to many of the elements in the periodic table as we go through other chapters. And today we're going to talk about what we call radioactive decay. And as you see right here, have a periodic table handy because this lesson will refer to the periodic table. Ready to begin? Well, first, we'll show you the periodic table once again here, and you should have your copy handy. We're going to concentrate some on the actinide series right here, this row going across the bottom, and also element number 104, rutherfordium. We're going to pay a little more attention to this element here, nobelium, and a few right here as well. So have your periodic table handy. You're going to need it as we go through this lesson. Ready to begin. First, nuclear radiation was first discovered with these things that weren't quite yet called X-rays, but got that name thanks to a man named Wilhelm Röntgen. And he has an element named after him. I think, if I remember correctly, Röntgenium, it is element number 111. In 1895, he studied some rays that a vacuum tube emits. We don't see too many vacuum tubes anymore because TV sets are so plasma, like your Roku TVs now. But a vacuum tube is a tube that is put in a vacuum. And I don't mean a vacuum cleaner like you clean the rug with. A vacuum is a space without air. Well, vacuum tubes, even though there's no air, there are no atoms, vacuum tubes allow electricity to flow through. And older style television sets, ask your parents and grandparents, they would use vacuum tubes and cathode ray tubes to put pictures on the screen. Well, in 1895, nobody knew very much about vacuum tubes, but this guy, Wilhelm Röntgen, he started to study these things. He noticed that many of the rays that came out of the vacuum tube glowed, light rays. They glowed when they hit specially painted paper. How he thought to do this, I have no idea, but he did. So these rays glowed when they hit specially painted paper, and what that caused to happen is the paint on that paper glowed even when not aligned with the tube's rays. So areas around those rays were starting to show images of certain kinds of objects. And you get a better description and a picture of it on page 176 of our textbook. But I'm not going to get too detailed into this, but just to show you, this was one of the first kinds of nuclear decay, radiation, that was discovered coming from the nuclei of specific atoms. Now, we didn't know at the time what these things were called, so just think in math, things that we don't know are called X, the X for the variable. So Wilhelm Röntgen, he called these unknown rays X-rays, and we still call those X-rays today. X-rays are great at showing things inside the body, particularly bones, to see if we have a fracture or a break. And that's something we're going to study in more detail later on in the year. Ready? Now, radioactivity. What is this energy called radioactivity? This happens when atomic reactions occur within the nuclei of atoms. Okay, if we say a single atom, then nucleus. Now, what kinds of reactions we'll talk about in a little bit of detail. Realize this is really a whole lot more complicated than we can cover in one little session of a 9th grade class, or 8th grade if you're in honors. Radioactivity, here's your textbook definition. Radioactivity is the emission of energy and protons from the nucleus, and I'll explain that better in the upcoming pages in just a tiny bit. Now see right there, this says greater than or less than, or it's actually greater than or equal to 84 plus 43 and 61. Now, element 84 is polonium. If you look at the periodic table in the textbook, you'll see the symbol for radioactive elements starting with 84 and going all the way through 118. But there are also two others. Element 43 is called technetium, also pronounced technetium, depends on kind of which dialect you have. And element 61 is called promethium. These are also radioactive elements, and These two occur both naturally and made in nuclear reactors, as we've mentioned before. Now, elements 84 through 92 are natural, but from 93 and above, those elements are made in nuclear facilities. But all these that are listed here, from 84 and above, remember, greater than or equal to 84, and 43 technetium and 61 promethium are all radioactive. And we'll see what that means in a moment. Now, radioactivity is also called radioactive decay, and there are three kinds that we'll focus on in this chapter. Radioactivity is also called radioactive decay. Ready? Now, what do we mean by stability? Atoms that are stable are not going to give off this nuclear radiation. See, we already know that atoms have protons and neutrons in the nucleus, but what holds those together? See, you have all these protons, something like uranium with 92 protons, and those are all like charges. They should be repelling each other. However, uranium also has a whole bunch of neutrons. The total mass is 238. So if we subtract 238 minus 92, we're going to get 146 neutrons also in a typical uranium atom. Well, a force, remember, all particles have a gravitational pull on each other. And so that force, that's called strong force, holding those protons and neutrons together, and that's when an atom is stable. However, sometimes remember that certain atoms have some extra neutrons, I should say. Remember, isotopes? That means the neutrons vary. Well, in atoms that have extra neutrons, those isotopes, the force may be too weak to hold all those protons and neutrons together. And what that happens, nuclear decay is going to happen. We're going to show you three kinds in a moment. And some of those particles are going to leave the nucleus until the atom becomes stable, which means no more decay is going to happen. So we have a strong force that pulls and holds protons and neutrons together in the nucleus, but if that force is too weak, likely because of extra neutrons, the nuclear decay happens until the atom becomes stable. So radioactivity is the emission of particles, protons and neutrons, or energy, or both. And it depends on which of the three kinds of nuclear decay we're talking about. So particles, or energy, or both could leave the nucleus. Ready? In nuclear decay, let's just list the three kinds on this page, and the next few pages will give a little bit of detail about each one. The first kind we'll talk about is called gamma decay. And in gamma decay, only energy leaves the nucleus, nothing else. No protons leave, no neutrons leave. Only energy in the form of gamma radiation leaves, hence the name gamma decay. There's one called alpha, in which protons and neutrons both leave the nucleus. And as you'll see in just a moment, 2 protons and 2 neutrons leave the nucleus. And the third kind is called beta. Now, I wrote protons on there, but I'll tell you a little bit more in a few minutes that also involves a neutron and an electron. But protons are the main focus for beta decay. So 3 types of decay: gamma, alpha, and beta. And the next few pages will give just a little bit of detail of each, because again, it's a lot more complicated than we're able to talk about here. Ready? In alpha decay, you see the picture on the screen. We have a parent nucleus. This is the one that's going to start splitting, as you see right here on the left. The daughter nucleus is what the atom is going to be left over, and the alpha particle is what is leaving that parent nucleus. Let me move this over, make that show up a little bit better. Okay, that looks better. The parent nucleus is going to lose 4 particles, tell you what kinds in just a second or two, and the daughter nucleus is what is left over. In alpha decay, the atom loses 2 protons. Let's just say the blues are the protons. So 2 protons and 2 neutrons exit the nucleus of the parent atom. Now, which atom has 2 protons? Remember, that's helium. So this is a helium particle with 2 protons and 2 neutrons. So a total of 4 mass units in that helium particle. So it's called an alpha particle, hence the name alpha decay. And we have a leftover nucleus. Now, that daughter nucleus will depend on what the parent nucleus is. So in alpha decay, an atom loses 2 protons and 2 neutrons for a total loss of 4, remember what AMU means, atomic mass units. And remember from before, both protons and neutrons have 1 atomic mass unit each. Now that 4 will be important for this reason. Here you want to make sure you're looking at your periodic table. We get a new atom which is 2 atomic number below on the periodic table. So let's just say this is uranium, element 92, that goes through alpha decay. Well, what's 2 less than 92? That is 90, and element number 90 is thorium. So remember, we have uranium-238. I'm going to draw the isotopic notation up here too. Okay, try to get a good contrast in color here. All right, uranium, which is atomic number 92, 238. Now remember, 2 protons and 2 neutrons leave. There becomes thorium. Well, the 92 has now become 90 because of a loss of 2 protons. That would mean 236 right here, but remember, also 2 neutrons leave. Remember, 2 protons and 2 neutrons. This means 238 minus 4 loses 4 atomic mass units. That's 234. So uranium-238 goes through alpha decay, becomes thorium-234. Loss of 2 protons, so 92 down to 90, but loss of 4 atomic mass units, total 238, 234. Now you might be tempted to say, hey, but thorium on the chart says 232. Remember, not all isotopes are the same. This would be thorium-234 because we started with 238 and lost 4 atomic mass units. That's going to equal 234. We'll get a lot of chances to talk about that and do some practice problems. Ready? In beta decay, take a look at the neutron given right here. Remember, this is a neutron, so there's no electric charge here. Okay. An electron has a negative electric charge, and a proton has a positive electric charge. Now, it's been a while, but we said some time back that a neutron is actually a proton and an electron stuck together. Make sure you can see the title on there a little bit better. A neutron is a proton plus an electron stuck together. So when this neutron splits, we get the proton and the electron. What will happen here is that electron is kicked out of the nucleus, gone, no more there. Realize we lost a neutron, so we lost 1 mass unit. However, we gained a proton, so we got back that 1 mass unit. That's like if Tom leaves the room and Johnny comes in, we still have the same number of people in the room, just a slight difference of the makeup, but still the same number of people. See the picture here? A neutron splits into a proton and an electron, as you see here. Now look at this thorium right here. Okay. This thorium-234, element number 90. Now because of this extra proton here, there's an extra proton in the nucleus. Well, look at your periodic table and you will see element number 91 is protactinium, Pa. Since there's a loss of a neutron, you would think that drops down to 233, but remember we gained that proton back, so 234, and that's why the mass will not change. So we're going to get a new element, but we're going to keep the same mass because all that happened was the neutron became a proton and each one has 1 atomic mass unit. So lose a neutron, but add on a proton. The electron just goes bye-bye, as you see right there. Okay, so a neutron splits into a proton and an electron. That electron leaves the nucleus. It is kicked out, it is gone. So as you see in this picture here, don't worry about the language right there. Just look at the numbers and the TH and the PA. Remember, chemical symbols, no matter what language, the chemical symbols are going to be the same all over the world. Example, thorium-234 becomes protactinium-234. Notice the mass is the same in beta decay. Because even though we lose one AMU, we get another AMU. All we do is we go up 1 on the periodic table. So 90 goes up 1 to 91, but the mass stays the same. Ready? Now look at gamma decay. In gamma decay, as we said a moment ago, I'm going to pause for a second. All right, back. As we said a moment ago, in gamma decay, only energy leaves. And you can see in the picture here, photons we've mentioned before are just light waves. Now this is a light wave that is very dangerous. It's a gamma particle, extremely high energy, invisible light, but very dangerous as well. This is helium-3. All heliums have 2 protons. This isotope has 1 proton. So remember, symbol, total mass. Helium-3 loses some gamma rays, some energy, but is still helium-3. No change in the atom or even the mass in gamma decay because only energy leaves. Yeah. Now, these gamma rays are extremely dangerous and extremely powerful. These rays can travel right through these concrete walls and they could kill us. They could kill elephants instantly. So imagine what they can do to us. The atom remains the same. There's no change in the protons. Well, if these rays are so dangerous and these rays come from the sun, why aren't we harmed? Well, God knows what he's doing. There's a layer called the ozone layer that blocks the harmful gamma rays and X-rays and highest levels of ultraviolet rays from the sun. Every now and then something kind of sneaks in though. The atom remains the same with no change in the total protons or the total mass. So again, take one more look here. Helium-3 stays helium-3 because only energy leaves that nucleus. Gamma decay can break atomic bonds, and that will cause other chemical reactions to occur, but gamma decay can be extremely dangerous as well. Ready? All right, now, something called a half-life. Certain atoms will decay, and some take many, many, many years. Some take very, very short amounts of time, a few seconds maybe, or a few minutes to decay. A half-life, you can guess what that means simply by the name. The time that's needed for half the atoms in a sample of a particular element to decay. So think of uranium. How long will it take for half that uranium to change alpha decay into thorium like we saw a little while ago? But we're going to use rutherfordium as our example here. In a half-life, 50%, half the atoms are now a new element, and 50%, half the atom, remain the original element, hence the name half-life. Again, half-life is a time needed for half the atoms in a sample to decay or change into the new atom. All right, we'll do some practice problems with this as well. So if you get it in the notes, great. If you don't quite get it, that's okay. You're going to get plenty of chances. Ready? All right, we're almost done, but here are a couple examples first. Here's an example of half-life using the element rutherfordium. Remember, Z means atomic number. So rutherfordium's atomic number is 104. Find that on your periodic table. It's in period 7. The half-life of rutherfordium is 78 seconds. That means after 78 seconds, half of that rutherfordium will have changed into something new. Let's assume alpha decay. Since rutherfordium is element 104, find element 102. You'll find that in the actinide series almost all the way to the right. Element number 102 is, take a look, you'll see it's nobelium. Okay. Let's look at 1 kilogram of rutherfordium-261. That's the mass of the atom. Remember, protons plus neutrons. Going through alpha decay, well, we know since alpha decay happens, we know what we're going to end up with. Rutherfordium, 104, 2 protons, 102 is nobelium. But remember, 4 total mass units, so 261 becomes 257. Don't worry about what the chart says about nobelium because we started with 261 and subtract 4. Now, what about the half-life? After 78 seconds, half of 1 kilogram, which is half a kilogram of rutherfordium, has now changed into half a kilogram of nobelium. Remember, the half-life of rutherfordium is 78 seconds. So after 78 seconds, a minute 18, half that sample, 1 kilogram to half kilogram, has now changed into nobelium, as you see right there. Okay. What if we let 78 more seconds pass by? Now we're actually going to start with the half kilogram here. Well, what's half of half? Half of 0.5 is 0.25. So after a second 78 second period, we now have half of what we started with here, half, which means 1/4 of what we started with here. Ain't it great? Okay, you'll see the equation and formula for it in just a tiny bit. But in this case, since 1/4 is still left as rutherfordium, that means 3/4 has now changed into nobelium. Okay, hopefully you can see that with the pink. All right, ready? This process is going to continue until all the atoms that could decay actually do decay. Decay is likely but not guaranteed. Okay? Not all rutherfordium-261 may decay. Possibly and likely to happen, but there's no promise about that. Remember, half-life means a time for half the atom to decay or change into a different atom. Ready? Okay, now here's the math involved. Here's a potential test question. How much original element remains after H half-lives? So I could say H is 4 or H is 5, and you'd plug in like in algebra, substitute the given value. Okay, let's look at the sample of the element. We have 5 kilograms of this certain element, and we're going to give this element 4 half-lives. Therefore, here's your equation right here. You might want to make sure you note this. Okay, let's make sure I get a contrast in color here. Here's your equation. The mass, which we're given here, half-life, 0.5 is half, and this exponent will be told how many half-lives. And this example is going to use 4. Okay. So what we're going to do, we're going to say our rutherfordium that we've been talking about, rutherfordium-261, we'll have 5 kilograms of this. This is always here. This is a constant, you see, does not change. And H is going to be 4. So we're going to figure out how much of this element is left after 4 half-lives. And rutherfordium is 78 seconds. So after 78 seconds passes by, 4 different increments of 78 seconds, how much is left? And all we have to do, you got your calculator, plug this in. 0.5 to the 4th power, as you see, is 0.0625. That's all we have to do. Or if you have a good scientific calculator, just type in 5 times 0.5 to the 4th, and we will get the answer. And that answer is 0.3125 kilograms. That is how much rutherfordium would remain if we start with 5 kilograms and let it go 4 half-lives. We'll have this much left over, less than 1/3 of a kilogram. That's a lot of the rutherfordium that has changed into nobelium. And just like with any algebra, we could get the answer here and figure out what H is. Okay, that involves a little bit higher mathematics though. All right, but we could do that if we know the math. Ready? You'll get practice problems with this. That is the end. There's my super hilarious the end joke. Don't decay while studying. All right, if you got it, great. If you didn't quite get it, that's okay. You're going to get chances as we do the practice problems. Good night.